I don't know. I'm a bit tired. It was very intense, but I hope that you enjoy it. So the previous in the previous lecture, I was talking about blazars, and they asked me to talk about supermassive black holes. They are super related, right? But so what I did is that I tried to separate the things mostly on the side of the jet, because when I think about a blazar, really, I think about the jet because that's what you mostly see when you look in radio and also in gamma rays. Is there? I mean, all the emission when we talk about these two bumps in the spectral energy distribution, and all that is coming basically from the jet because you don't see much, except, well, you also see other stuff, but it's mostly the jet. So today we will try to look with a little bit more detail about the central engine, because in the heart of every blazar, in the end, there is a black hole. So we'll talk about that and give some of the properties that these black holes have and other things that you can measure with them. So not only the jet. So that's what we will do today. So we'd like to start asking what's a black hole, right? And a black hole has, the definition that I like is something you can think about them physically, and a black hole is an object so massive that nothing can escape its attraction. And that's one. And the other, that's one definition, like an operational definition. And some people were doing this side of game very early, like many years ago, even before relativity that predicted them. And I don't know if you have done this exercise. If you compute like the energy of a black hole, of a mass orbiting a large mass, right? You can make that computation, and you balance the kinetic energy with the gravitational energy, and if you put the velocity c, you get the Schwarzschild radius. It's just a coincidence, but you can do that game. You can also do the computation of the deflection of light just by doing some conservation of energy, and you get the right result except for a factor of 2. So there is something there that people suspected that these objects will exist, but they weren't predicted by the Newtonian gravity, of course. And then the other way to look at this is to look at the mathematics, right? And I'm showing this book because like a couple of years ago, I was reading this article in Physics Today. I don't know if you read, do you read Physics Today or not? How many of you read Physics Today here? Not many. So it's actually a good idea to read Physics Today. Like I will just, I mean, I don't read it so much now because I have a family and lots of things to do. But when I was a student, I used to read it a lot because, I don't know, the ones that have read it, you can learn about many other things. So it's sort of like a magazine, a general science physics magazine for like scientists. So for example, you can learn lots of things about other fields, and I actually like it. And I still try to read it, but I don't read like the super long articles. I read the short ones. So there was one about the 50-year anniversary of this book. How many of you know this book? Okay, good. So have you used it, or you use it? Yeah. Some people like it, some people don't like it. But it's a huge book. So it's a huge book, and it's sort of like the classic of general relativity. And as I said, like so the book talk about like how some people really hate this book because it's so long. It's sort of like this. I don't know if you know the other book that is so long is the Cohen-Tanucci, the quantum mechanics. That's so long. Yeah, I probably read like a tenth of it. Well, that's probably enough for most people. But so the thing is that these are how we describe black holes with gravity. And I actually have, I didn't like this book when I was a student at first as an undergrad, but as a grad student, I took general relativity from Kip Thorne. So I actually have to use it. And it's kind of fun. I mean, it's full of these quotations that are sort of like historic quotations, and it has some humor in between. It's kind of fun. And also, Kip Thorne has written some general public books that are also very good. I don't know if you like that. Okay, so when you want to look at a black hole, and I'm not. I will talk about a little bit just about this because it's not that I remember a lot actually. So even if I took the class with Kip Thorne, I don't remember a lot because I don't use it, right? Because I'm an observational astronomer. So I'm mostly based on this book. The Mayer wrote a book about black holes and about AGNs, and you know that when you look at an AGN, you also have some analogs to the AGNs that are the microquasars. The microquasars are very similar to AGNs. And all the phenomenology and the accretion disk and the jets and all that is very similar. The only difference is that when you look at microquasars, you see they change state very quickly because they are much smaller and all the time scales. And we won't talk about time scales here, but when you have a time scale, you can imagine a very simple way to get a time scale for accretion is to compute the time that a particle goes around in an orbit. And if you are in a small object, the orbits will go quick. and in a large object, the orbits take much longer. So everything that you see in an AGN that takes millions of years in a stellar mass black hole is very fast. So you can look at these sources and you see them throwing jets, then they stop throwing jets, the accretion disk changes, and things like that. And all that is very well described in this book. It's another huge book. And I also have some personal story with this book because Dave Meyer is a researcher at JPL, and he has been reading this book for like 20 years. And one day we were talking, and he told me, "Oh, you know, Walter, I'm reading this book, but I cannot finish it because I need to like go to the details of that." And with my classmates, because it's the type of thing that you do when you're young, I said with one of my classmates, we said, "Okay, we will read it. We will find all the typos and all the problems, and we will help you publish this book." And we spent a year reading this book with him. So it was a very nice experience because it's a huge book. And we actually got Dave to finish the book. I mean, all the book was perfect, but there were many typos as in anything that you do. So we helped him with that, and we even got our names in the acknowledgements. So let's go back to the real thing. So when you look at general relativity, what you do is that you have the equations, right? So these equations, they look very simple, but in the end, you know that they are full of many things inside. The Ricci tensor, Ricci scalar, and all these things. But in the end, this is the equation. So you have, in one side, you have the terms that describe the geometry, and that's how you describe the geometry. These are just combinations of that metric tensor. And on the other side, you have the stress energy tensor that really tells you the distribution of matter and whatever is going on. So that's what you do. And you equate the two, and you end up with like 20 equations. Is it 20 equations? It's like 20 equations that they are nonlinear, really complicated. But in some cases, you can solve them. And so this is the simplest solution, is the Schwarzschild solution, and you actually put t equals 0 because there is no matter, and you just find an isotropic solution. And it was found like 10 years after, no, it's like the year after, right? Because 2015 was 1905 was the special relativity. So, and you describe these terms, and you see that something funny happens when you reach a certain radius, that is the Schwarzschild radius. And of course, you can change the coordinates and blah, 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 but these are the coordinates that you usually use. And you find that there are some special places in this mathematical object, in this isotropic solution. And one is the Schwarzschild radius. And in this radius, basically, what you find is that there is what is called an event horizon, and once you cross that, you cannot go back. And there are other important points in the black hole that we will describe later, but this is a very important one. And this is very different from any other object, right? Because once you get down there, you fall to the center and you go to the singularity. If we look at the scales for the objects that we have, normally when we look at the supermassive black hole, we are talking about a mass of 10 to the 7 up to 10 to the 10 solar masses. So we normally write the equations in a way that we sort of normalize by an average mass of 10 to the 8. And the Schwarzschild radius for a 10 to the 8 solar masses object, that is an average supermassive black hole, is 3 times 10 to the 13 centimeters. And that is about 2 astronomical units. Okay? So that's sort of like the scale that we are looking for. So if we look at a 10 to the 8 solar mass black hole, we are looking at a black hole that is 2 astronomical units. And everyone knows what an astronomical unit is here? No? Okay. So I still put together a quick slide about this. So if you don't remember, an astronomical unit is basically the radius of the orbit of the Earth. So it's about the size of the solar system, so to say. And then we have the other unit that we use a lot is the parsec, and the parsec has to do with astronomy. So when we move during a year, the Earth is separate. The maximum separation of the Earth in one point of the orbit and the other extreme is 2 astronomical units. And if you look at the stars, the distant stars don't move, but if a star is close by, you will see the star moving. So you measure the parallax, and the way we compute distance is 1 divided by the parallax. So that's why you call it it's parallax of seconds of parallax or something like that. That's the origin of the name. So the farther the object, the smaller is the parallax, and then the larger is the distance in parsecs. So in the end, a parsec, an astronomical unit is 1.5 times 10 to the 13 centimeters, and 1 astronomical unit is 8.4 light minutes. And that's important because you remember that in the previous talk, we said that some sources vary in the very high energy gamma rays in a time scale of 2 minutes even, or 10 minutes. So that means that they are, so with this, we can get an idea of the size of the source. So some sources are as small as the orbit of the Earth. So that's basically the number to keep in mind. And that's huge, but you have to think that in that region, you have a black hole of the order of 10 to the 8 solar masses. And here we have only 1 solar mass. So it's a huge thing. And then for the parsecs, we are talking about 10 to the 18 centimeters. So it's 1 parsec is about 200,000 astronomical units. And 1 parsec is also 3.2 light years. So that's a much larger distance. So that's the simplest solution. And then the other solution that is usually used in astronomy is the Kerr solution. And the Kerr solution is the same as we had before, but now the black hole is rotating. And if you look at this in Newtonian gravity, if you have a central mass that is rotating, it doesn't make any difference to the outside, if it is symmetric. I mean, if you have perfect symmetry, you will not see it from the outside. But in general relativity, it turns out that it drags the space. So you get some effects that are not classical. So that's completely different. So the metric here is much more complicated. You don't need to remember this, but you need to remember a couple of things. One thing is that we usually parameterize the angular momentum by this factor that's called J, and in some places it's called A. So, but it's the same thing. So basically, the sense of direction is relative to the matter that you have outside. So you can have it rotating one way or the other, and then the gravitational radius that is half the Schwarzschild radius. So that's for the Kerr metric. And if you look at that, you still have an horizon. You have a horizon, but the horizon now, it depends on the amount of angular momentum you have. So you can have the horizon. If you have 0, if J is 0, you have the same the same horizon that you had before, but otherwise the horizon is a bit closer, right? Because this is subtracting from 1, so it gets closer to the source. And you also have the ergosphere radius, and the ergosphere radius is basically the radius that there is a region of space where the space is being dragged by the rotating black hole. So that's that region, and you can see that it's smaller. It has a smaller radius near the poles, and a larger radius near the equator, because the effects of rotation, you cannot feel them in this part. So that's all we need to know for now. There are solutions for charged black holes, but we never use them in astrophysics, because what happens is that if you ever have this is the idea. I mean, some people, I was reading some papers the other day, and some people were arguing that you could have charged black holes in astrophysics situations, but they are probably transient. But the idea that we have, and what we suppose is that if we have a charged black hole, there is a lot of charge around, so it will neutralize very quickly. So most people don't care about the charged black holes. So we only look at the Kerr solution. And the Kerr solution actually contains the Schwarzschild solution as a special case. So another thing that is important for black holes is that you can have orbits. So in the same way that you describe the orbits in Newtonian gravity, you can describe the orbits here. And usually what people do is that they use the same type of arguments that you do for Newtonian gravity, but you define effective potentials. So you modify the potential. So in the end, once you get to this point, to the point of solving orbits and all that, it's sort of like a classical problem. You are not dealing with tensors and all that. You just deal with a potential, with an effective potential, and you solve the orbits. And you can have orbits for particles and also for photons. The only difference being that photons go at c and particles go at speeds smaller than c. And there are a couple of special orbits. The most important one for our purposes is the innermost stable circular orbit. So in Newtonian gravity, you have stable orbits because it depends on how much angular momentum you have, right? So that's how you define an orbit. And here is sort of like the same, but there is you cannot go all the way in, because at some point you hit the maximum speed and you cannot go faster. So that defines the innermost stable circular orbit. So that orbit is the closer that a particle can get in a stable orbit to the black hole. And that's going to be very important, because if you have matter that is falling into the black hole, the matter will orbit happily, but at some point it will get to the ISCO, And once it gets to the ISCO, it cannot go deeper. Once it goes deeper, it will just fall down. So it's a very important orbit, and we will talk about that. You can see here that I deleted one column because there is something that we can deduce from that. Because when you are throwing matter, it is a very different thing if you have the matter orbiting and radiating on the way there, or if it's just falling down. And again, I'm trying to, I did this in the other, so I think that we will put these slides in the website at some point, but I'm putting some references here. So this is a general AGM book that has a lot of this discussion, but concentrates on the parts that are relevant for AGNs, for active galaxies. Because, for example, gravitation is a theoretical book, right? You will only read that if you wanna, if you enjoy the math. If you just wanna use them if you're an astronomer, you will probably look at a book like this. So the next question that one can ask is, where do we find black holes? And there are two places where we find black holes, and one is in the end stages of star formation. So when you have you know that stars have lives, right? So the stars are born in star formation regions, and they are formed when matter collapses, and then once they start producing energy by nuclear fusion. They stay for a long time. Well, the most massive stars evolve very quickly. The lighter stars live for longer, and they evolve and they produce energy in the main sequence, and after that they die. Some die as planetary nebula, the lower mass, but the high mass stars, they explode as supernovas and end their lives as neutron stars, black holes, and they also gave some of the material back to the interstellar medium, and that's how you enrich the molecular clouds with heavy elements. So that's the cycle, and that's how and that way we can produce black holes all the way to up to 30, 40, 50 solar masses. So there are some black holes that LIGO has been finding very massive black holes, a few of them, but you cannot go more than 100. So because there are some problems with you cannot go up because the star basically explodes. So you cannot produce more massive black holes. So that's one way, and the other place where we find black holes, of course, are galaxies, in the center of galaxies. And here I'm showing some movie. I don't know if you have probably all seen it, because this is a movie of the stars that are going around the Sagittarius A star, so the center of the galaxy. What they did is that these are the data taken by the UCLA group. And what they did is that they followed the stars for 20, 30 years, and they get the orbits. And from the orbits, you can get the mass, right? It's just basic dynamics. If you are far away, Newtonian gravity is a good approximation. If you get closer, you start looking at relativistic effects. But for this measurement, I think that the relativistic effects were not so strong, but they can still get the mass. And they got a Nobel Prize for this because it's tough. It's a tough observation because the galactic center is a very complicated region. So it's not that you can just point your telescope and look at that. In optical, you cannot see anything. You just see the clouds. But you need to do this. This was done in the infrared. And in the infrared, the resolution is worse because you know that when you have a telescope, the resolution that you get from the instrument depends on the size of the telescope. The larger the telescope you have, the larger the resolution. And also, the shorter the wavelength, you have more resolution. But when you go to the infrared, you are going the opposite way. You are going to longer wavelengths. So it's harder to resolve. So they needed to develop some new techniques to get to this type of resolution, including infrared interferometry and things like that. So there in the center of the galaxy, we have a black hole that has this mass of 4 times 10 to the 6 solar masses. We also have black holes in radio galaxies and blazars, right? But those are even more massive, 6 times 10 to the 9. That's almost 10 to the 10. So those are, we already talked about them, so we will not say much more. So then the question is, how do these black holes radiate? Because we know them, we know that they emit radiation, but they don't, right? We know that they don't emit radiation, but somehow we get to detect them. Because even if they don't emit radiation by themselves, they are accreting matter. And that's how they radiate. There are many, the subject of accretion is a whole world. So when you study this, you start studying what is called Bondi accretion, that is sort of like a spherical accretion, accretion with a spherical symmetry. But since in most places the matter is rotating, there is some rotation, in most cases you form an accretion disk because the matter is trying to fall down, but since it has some angular momentum, it cannot fall, and it settles in a disk, and it stays there. So the main way to accrete matter is to form an accretion disk. And when you are forming that matter, the matter is trying to fall down, and you have a central source that is producing energy. So an important quantity, and this is an important thing that we compute, is that you have the central object that is producing radiation, and it's also pulling that particle. This is a small particle of gas, of dust that is trying to fall down into the source. So it's being pulled in by the gravity, but it's being pulled out by the radiation force. So basically, you have the radiation pressure, and you have some scattering there. It's like the Thomson cross-section. And you can compute that, and you get a radiation force. And if you equilibrate that, you equilibrate the radiation force and the gravity in a particle, you solve the equations, and you get to an equilibrium point. So basically what happens is that if you have too much, the gravity is fixed because the gravity is given by the mass of the source, but if you have too much radiation, the particle will be pushed away. So basically you have a source that is too bright, it cannot accrete. So a source that is too bright, it will just push the matter out. And the maximum value to be able to accrete is what is called the Eddington luminosity. So you can compute that value, and this is what you get. I mean, it depends on the scattering cross-section because you have a charged particle, and that's how they interact with radiation. You also have the mass of the central object and some factors here and there. This is the mass of a proton, and this is the mean molecular weight. So it depends on the composition of your gas. You can have helium. If you have only helium, that's probably be close to 1. But if you have heavier elements, you will get a larger factor here. But this is the thing, basically. So if you can compute that luminosity, and that luminosity for a solar mass object is of the order of 10 to the 38. So it's a number that we always keep in mind. So you can have so basically that means that if you have an accreting object that has more luminosity than the Eddington luminosity, that is a sign of trouble because that object shouldn't be accreting too much mass. It still can accrete because there are ways for you can avoid, for example, if you have a smaller cross-section for this interaction, like the Thomson cross-section, you can avoid that and you can still accrete, but that's normally a good order of magnitude estimate for the maximum luminosity. And then you can also compute, if you have the luminosity, basically that luminosity must be coming from somewhere. And what we assume is that the luminosity is coming from the matter that is falling into the object, right? So basically you can divide the luminosity by the amount of matter, and you can get an accretion rate. So you convert the luminosity in an accretion rate using the MC square formula and an efficiency. So this efficiency, we will compute it later, but it's usually from a few percent to up to 42%. That's the maximum. We will say more later. But basically, you can the maximum accretion rate that you have with a 10% efficiency for a 10 to the 8 solar mass black hole is 3 solar masses per year. So it doesn't seem like a huge number, but that's all you need. And then there is another important thing is the Eddington time. And that's the time that a black hole takes to double its mass. So if you have a mass of m and you are accreting at this rate, you will double your mass in this time because the black hole grows, right? And that's another thing that we need to figure out. When you throw matter into the black hole will grow because the matter is falling. And that time scale is 400 million years, right? So so this is a good time scale to keep in mind because sometimes when we hear in the news, for example, they said like, oh, they found a super huge black hole at redshift 10, and you know that redshift 10, the universe is not so old. So that tells you that you cannot form a deep black hole by accretion because the time scales are this big. So it's a good number. It's another good number to keep in mind. So then, when you look at the accretion disk, as I said, this is a very complicated subject, but the most basic model of an accretion disk is a disk that is geometrically thin and optically thick. So basically, when we talk about optically thin things, we are saying that it's transparent to radiation, and optically thick that it's not transparent, that it has a surface. And this is the most basic model that we have for a black hole, and you can solve the equation. It's just the hydrodynamic equations. Not saying that it's easy, but it's something that we can do. And it's because when you do that, you can ignore some, for this solution, you can ignore the self-gravity of the disk. You only care about the central mass, and you throw particles around that. And when you do that, you can find the velocity profile of the disks. And normally, if you don't have any dissipation mechanism, the particles will stay there forever. But the particles need to fall for some reason. And what happens is that in these disks, if you just look at the Keplerian disk, you will see that the velocity will reduce as you go out. So the particles that are farther out are moving slower than the ones that are inside. So that interaction, if you have some viscosity, you can transfer energy. And you can get rid of the angular momentum, and the particles can fall. And also you will get dissipation. So the gas will get heat, will get very hot in this disk, and it will radiate. But what you do to model that is that you take annually a different radius, and they get a temperature. You can compute the amount of dissipation that you are having, and then you use the Stefan-Boltzmann law, the sigma T to the 4, and you can compute the temperature of that annually of gas, and then you get your spectra. So you get this profile. So basically, you get a profile that the closer that you get to the black hole, the hotter that the matter is. So that's why, at some point I said in the previous lecture that if you look at the stellar mass black hole, they radiate a lot in the X-ray, because the matter can get really close. When you look at a supermassive black hole, you don't get to the X-ray, you only get to the UV. So they are in a different regime. And then what you have here is that you have a spectra that is composed of many black body. So really what you're looking for, what you're looking there, you have this spectra. This is the spectra of the accretion disk, and this is the hot corona. This is some gas that is around the disk. But you have a collection of black body for different radii. So when you're looking at this part, the nu to the 2, that's basically the black body part of the spectrum. And this is the lower energy part. So it's the gas that is farther away. So that's the gas that is very far away, that is not so cold, right? That is not so hot. So this is the outer radius. And then you get to this part, and this part is sort of like the inner radius, right? And that profile, that part here is just the addition of all these components. So basically here, from looking at this part, you can tell how big the disk is in the outside, and here you can tell how closer you are getting to the black hole. But of course, this simple model that you can solve in a couple of hours is not so great, right? So there are more complicated models, but this is the basic idea. So so this is the model that we just showed, but in some models, for example, in that model, in the simple model that is called the Shakura-Sunyaev model, in that model you assume that you are radiating all the energy. It's very efficient. But in some cases you cannot radiate all the energy, and the gases start to get really hot, and when when the gas gets really hot, you get a lot of pressure, so you sort of like get a thick disk. So you have these different disks that depend on how much you are accreting and how efficient you are at radiating. And this is a whole subject. So you can go crazy studying different types of accretion disks. But the main idea is that. At some point, people have to start simulating them. So that's the point. I mean, the point is that this simple model is something that you can solve with pen and paper. But for the other models, I think that you need to simulate them. So now we can talk about the efficiency. So what happens when you have the accretion disk is that you have the central black hole and you have the disk around. And as long as matter is doing this, it's getting hot and it's radiating. But once it gets to the innermost stable circular orbit, it will just fall down. And once it falls down, it can radiate a bit, right? Because there is also a stable orbit for the photons, and it's inside this one. So it could radiate a bit, but it's not so much. So basically, what we assume is that once you get to the ISCO, you will just go into the black hole, and you will make the black hole grow, but you will not produce more radiation. So basically, the closer that you can get to the black hole, the more efficient the black hole the central engine is. So that depends, how close you can get depends on the amount of rotation that you have. So here is for the Schwarzschild black hole, and you can get to a radius of 6 gravitational radius. So that's the ISCO radius. But if you have a counter-rotating black hole, you can get to 9, so it's farther away. And if you go to a black hole that is maximally rotating, that is 0.998. So you cannot have a black hole that rotates at 1.0. So there is a paper by Roger Blanford that shows that it's sort of like a, well, is it Kip Thorne? But one of them. So there is a maximum energy that you can get astrophysically. So it's sort of like this maximum. But theoretically, you can get that, but astrophysically, it's really hard. And from that, what you do is that you assume that you have some potential energy in infinity, and then you go to the ISCO, and all that energy, that difference is the energy that you can radiate. That's the maximum, right? If you are very efficient at radiating. Because basically, you get rid of the gravitational energy, and you put it as radiation. So the closer that you can get, this is larger, and that's the reason why when we have a Schwarzschild black hole, we get an efficiency of 0.0, well, this is 1, so this is 5%, 6%. So we have a 6% efficiency. And when we go to the maximally rotating black hole, we get to 42% efficiency. So that doesn't sound so extreme because, for example, when people talk about solar panels, they said that solar panels have an efficiency of 10%. But there is a trick. The 10% is only accounting for the radiation that you get from the sun. And here, the maximum is the total energy of the particle. So it's this MC square factor. So this is so to say, is a maximum because it's all the energy of the particle. You are even accounting for the mass of the particle. So that if you compute that factor, it's not comparable. That's what I'm saying. So if you do that, for example, for nuclear fusion, that is sort of like our next hope for having more energy. The efficiency is 0.7%. So what this means is that the most efficient engine that we have in the universe are AGN. So if we ever want to have, I don't know, conquer the galaxy and have lots of energy, we will need to learn how to extract the energy from black holes, from AGN. So that's for the theory, and then for the accretion. But you also know that when we have black holes, we also see them because they emit jets. And we already talked about that, but we never say what was going on there. But I think that maybe Elizabeth or someone else said something about this. But the basic process, the basic ideas that we have, the basic mechanism for the production of jets is this Blanford-Snajek mechanism that was proposed in 1977, only using paper and pen. And the basic idea is that you have the black hole in the center, and you have an accretion disk, and the accretion disk is bringing these lines of magnetic field. So it's bringing this magnetic field inside, and then the magnetic field goes close to the black hole, and it's being dragged by the rotation of the black hole, and that somehow pushes the material away, and that's how you produce a jet. And that's the main idea. This is a very important paper, and I look at the reference, the citations yesterday, and it already has 3,100 refereed citations, almost 4,000 total references, and it's going strong. And this was done on paper, right? Like the old theory from the 70s. But now people can simulate this in supercomputers. And basically, and I put this figure from a Kwan, Dai, and Chekhov's paper from last year, using what they call general relativity magnetohydrodynamics, so GRMHD. They couple the equations of general relativity with magnetohydrodynamics, so that sounds complicated, and it is complicated, and that's why it took so long to do it. But if you look at this plot, I like this figure because it basically looks like that. So it's amazing how they could have all that idea in 1977. And they can even simulate the dynamics. So it's hard, but for example, in this paper, I think that they simulated like an orbit of the material at some radii. It's just really cool because they are getting to the point of simulating this. And in the end, this is what we want, right? Because in the end, for example, when we look at the variability of the sources, what we would like to know is to have a simulation like this. That is, here they are only showing the magnetic fields and the matter. So they still don't include radiation. At some point, they need to couple the radiation. What they do with the radiation now, my understanding is that what they do is that they take this solution and they put the radiation sort of like after the fact. At some point, you need to couple it with the radiation and also with the particle acceleration processes. But that's way too much. But they are still not getting there, but at some point we will do it, hopefully within my lifetime. Or maybe you will do it. So that's still going strong. And the other thing that we can learn from jets, and we can look at the observations of jets, and I mentioned this very quickly, but I wanted to show you this paper that I found really amazing. So this is the jet of M87 at different scales. So this is 1.6 gigahertz, and then they zoom in this area, and they do another zoom. So basically they can get it in a very large range of spatial scales. And they can measure the jet. So this is the distance from the core. The core is this part of the jet in Schwarzschild radii. So they can get all the way to 10 to the 7 and very close to the black hole, like 100 Schwarzschild radii. So it's very, very amazing. And one of the things that the theory always predicts is how these jets are launched. So what they see here is that there is a transition. You see that this is a log-log plot. So when you look at a line here, you are basically looking at a power law. So what they see here is that they have a power law for the size of the jet. So this is the aperture of the jet. So basically what they measure there is that they take the VLVI images and they measure this. If you have the redshift, you can measure the angular size and then you get the size. So that's what they measure there. And they see the profile of the jet and it changes at some point. And this Bondi radius is a radius where you have the speed of the particles around the black hole and the sound speed. Okay, they equate. So at some point, there is a transition. So in this part, the jet is growing like a parabola, and then it's just a cone. So it tells you about the acceleration of the jets. So what else can we do with the jets? We can measure their masses. Sorry, with the black holes. We can measure the masses, and what you do is that you model the stellar kinematics. If you have a central black hole around and stars going around, if you measure the dispersion of the stars around, you can get an idea of the mass just by doing basic Newtonian gravity, because you are so far away that it doesn't really matter. You don't need general relativity. You can do the same with the gas and even with mega masers. So masers are the same as lasers. Actually, masers were discovered before lasers. And you can have the masers and you can construct this profile of the speed, and you can see the Keplerian speed and all that, and you can get the mass. It's a very interesting stuff. One day, this is another story. You have many stories when you are old. I was watching a talk by I forgot his name, but the person that discovered the masers, and he had trouble using a laser. It was so cute because he was like 90 years old and he couldn't figure out how to use the laser. So another way to measure masses for these black holes is reverberation mapping. And I also mentioned it before, but I wanted to show it more properly, because I don't know if all of you knew about this. So what you have is that if you have this is sort of like a model of a cloud, and if you have a cloud and you have some radiation here, if you send radiation here, the radiation will bounce of the clouds, and these are the contours the contours of equal time. So all this region will take the same time to go back to the origin. So basically, it's the idea that I described before, right? That you have the central black hole, and you have the clouds going around, and basically you get the continuum, and after that you get some line variation because the line takes a little bit of time to go to the cloud and then come back. So this delta T tells you about the size of the region. So what people do is that they actually look at continuum variation. So these two plots, these two curves are the continuum, and these are lines. This is the flux in Lyman alpha and H beta. And you can see that the profiles look very similar, but they are delayed. So it's hard to tell here, but what you do is that you cross-correlate the light curves and you find the delay, and from the delay you get the size of the road line region. From the width of the lines, you get the dispersion, the velocity dispersion, and you can compute the mass using this equation. This is just Newtonian gravity again. The main problem is that this method is very good, but there is this factor, this F factor, that you probably know about that. That's why you laugh, because that's where you are hitting all the details. So basically, you don't know how you get an average value for the delay, but you know that you don't have a single delay, right? Because some clouds are closer, so you will get a smaller delay. some clouds are farther, so you will get a larger delay. So the broad line region could be flat, or could have like it could be an outflow. We don't know. So basically, all that is hidden here, and people always said that this is a factor of ordered unity, but it can be large. So there is some uncertainty in the masses that you get from reiteration mapping. Anyways, people have used it because although it's an expensive technique because you need to monitor the sources, you can still get masses for black holes that are very far away that are not resolved. Because all these techniques, for example, if you want to measure the stellar kinematics or the gas kinematics, you really need to resolve the source, so it has to be very close. And for that one, you don't need to resolve the source because you are only looking at the time variation. And people found also that if you take the luminosity of the source and this is the luminosity, this is the radius, there is a correlation. So now, if you have the luminosity of the source, you get a good measurement of the radius, just with one measurement. So doing reiteration mapping, you need to follow the source for a long time. And the more massive the source, the longer are the delays. So it's hard to measure this for a very large black hole because you need to monitor for a very long time. But you can do single epoch measurements using the RL relation. What else can we do? We can measure the spin. And how do we measure the spin? Is that we don't only have an accretion disk. We also have, in these sources, we have a corona of X-ray that is emitting X-ray. So it's a ionized material that is emitting a very hard spectrum, and it's the one that I will go back here. And basically, when you look at the X-ray, you see this additional component. So this is the hot corona that it's emitting. It's a very energetic place. And that radiation is above the accretion disk. So some of that radiation will hit the accretion disk and will bounce. So it's called reflection emission. So it's sort of basically and what you get is that you get these lines of these X-ray lines from iron, the 6.4 keV, and these lines has a very weird shape because it's determined by the rotation of the accretion disk. And this is a relativistic effect, actually. So from the difference in the profiles, they can measure the spin. So that's another thing that we can do. One important thing that we observe when we look at these black holes is that they follow a close relation. So this axis is the dispersion of stars. So you look at the galaxy, and the galaxy has its own stars going around. And this is the dispersion, the velocity dispersion of the stars in the galaxy, and this is the mass of the black hole. And they are very well correlated. This is an old plot from 2002, and people are still filling this diagram. And it's very amazing how well they are correlated. You can also correlate that with the mass. So you can use I'm not showing it here, but you can use the dispersion of the stars. It's also correlated to the mass of the host galaxy. So in the end, this means that you have a correlation between the mass of the black hole and the mass of the host galaxy. But the black holes are very small. We already saw that the black holes are of the order of the size of the solar system, but the galaxies are huge. And the main question here is that, well, these are connected, obviously, right? Because if you have a larger black hole, you have a larger host, but we don't know how. And this is another active field of study. So people talk about, for example, how when these active galaxies accrete material, they will produce lots of radiation. So the way galaxies grow is that they accrete other galaxies, right? So they accrete material, and that's how the black holes grow. But if you have a lot of radiation going out, you will stop that process. You also have the jets that can stop the process. So there is some feedback mechanism that is sort of like regulates the growth of the galaxy and also the black hole. And that's another story. So then we can also ask how these black holes form, and there are many ideas. But basically, you can look at this recent review that is actually very good. But the main idea is you need two elements. One element is that you need seeds. So you need to start with some mass, some big mass, and the main ideas that people have are supermassive stars. So when you have the first stars, they can be very massive, and you can start with a few hundred solar masses, and then you start like putting all. So that's how you start. You can also start with more normal stars, but then they merge, as we have seen with LIGO, right? They start merging, and then that's how you get your seeds. And there are more exotic ideas like primordial black holes or cosmic string loops and blah, blah, blah. So those are the seeds. And then after you have seeds, you need to start making them grow. And how you make them grow? One is accretion. One way is accretion. If you have a big star surrounded in a big molecular cloud, you can start accreting that material, and that will give you only so far, right? Because you have this Eddington time scale, for example. You cannot double the size of this very quickly, because if you suck too many material, you will also produce a lot of radiation, and you will stop that process. So it's complicated. So at some point, you need to start having mergers. So you will have mergers between these galaxies. And this is the model that we have for the hierarchical galaxy formation, right? That's how we think that galaxies are formed. So since we think that there are mergers, a lot of people are trying to find binary black holes. Why? Because, I mean, that will be a proof that we actually have mergers. And we have seen galaxies merging, but all the examples that we look in the optical, they are galaxies that are very far away. So what people are trying to do actually is try to get examples where the black holes are closer. And one good example is this source, OJ287. That is a VL lag at redshift 0.3. And for this source, they have a light curve from all the way from 1900. So like more than 100 years of data. And you can see that it has some flaring episodes. And it turns out that these flaring episodes are periodic. So they have some regularity. And this is a, doesn't working. Doesn't work. Okay, now it's working. So this is an animation that they make for an Spitzer paper where they monitor the source, because the flares are so regular that people predict them. So there was a prediction for this, and they were waiting for the flares to see if the prediction will come true, and it actually came true. So the model that they have for this source is that you have a binary black hole, and the smaller black hole is actually hitting the accretion disk, and that's how you get the flares. Well, you can look at that later, but basically this is the model that they have. They have a black hole of 10 to the 10 solar masses, and the smaller one is 10 to the 8, and they have a period of 12 years, but with double flares. Another case where you can see these dual AGNs, many people search them for the emission lines. You know that if we have two galaxies that are merging, we expect to have two broad line regions and two narrow line regions. So if you see double lines, people always suspect that those are galaxies that are merging. The problem is that you can get double lines with outflows and with other things. But still, people try to follow them, and they observe this one. They have these lines that you see that it looks double here. So they look at that candidate with BLBI, and they actually resolve two cores. And these two cores are separated by 7.3 parsecs. So these are very, very close. This is the best example that we have of a binary black hole. And another one that we found with you remember that I told you that I was working in this monitoring program in the radio band. So this is an example that we found in our data. Normally, when you look at the light curve of a blazar, you don't see any periodicity. They are just super random. And actually, the only thing that we do to characterize the variability is to measure the power spectrum. So we take a Fourier transform, and that's it. That's all we do, because they are not regular. When you see a blazar that is regular, there are a few examples, a couple in gamma rays. But they usually have a couple of cycles. So for example, when we look at this example, this source, PKS 2131, the blue are our data. So this Sandra O'Neill, she is the first author of the paper. She was an undergrad at the time, so she was giving this project as a toy project for the summer, but it turned out to be something very cool. So she was looking at that, and it was, okay, we have 1.5 cycles. So no one was super excited in the group. We said, okay, maybe because you can get that, it can be a fluke, just a spurious variation. So no one takes very seriously a cycle of 1.5, a light curve that is periodic with 1.5 cycles, because you publish that and people think that you're crazy, right? So, but what Sandra did, she was very industrious, and she started looking at the literature and data and more data, and she found more data in the source from the 80s. And in that data, you can also feed a sinusoid. So you also see that you have one period. But the amazing thing is that if you take the period here and you propagate it all the way back to here, and you do the opposite that, they match. So these are the different light curves. So they match the match of the period and the phase is better than 10%. And that's amazing. I mean, that's amazing, because these are completely separate experiments. So that's why we actually believe that this is a real periodic source with a real binary black hole. And we have this model. The model is that you have the jet, and the massive object in the center, and the other object is moving around, but the massive object in the center is also moving. So it's actually changing the the Doppler factor a little bit because it changes the angle of vision. So that's how you get the period. And you can get the distances that we get here, the orbital separations are really, really, really close. But still, once they get really close, they can start radiating, producing gravitational waves. And we have tried, we talked to the people that look at that with pulsars. I will tell you more about that in 1 minute. But they haven't detected because these experiments, they are not very sensitive yet. But this one should coalesce in like 10,000 years. So still, we won't see it. But I will leave the task to my daughter. So they will pass it generation to generation. Maybe one day they will see the coalescence. So that's the story. So you have, this is an image that I took from nanograph, and I will tell you more about that from Sarah's Polar. And what the idea that we have is that we have galaxy mergers, and then once the galaxy merge, they start to get closer, and at some point they will coalesce and they will produce gravitational waves. And we have seen this for stellar mass black holes with LIGO, right? But the idea now, people are trying to do this with pulsar timing arrays and also with space interferometers with LISA. These are the experiments that we have, the pulsar timing arrays. What they do is that you know that pulsars are very regular, but sometimes the pulsars, there are some residuals in the timing. So they see that the pulses come a little bit earlier or a little bit after. And if you look at many pulsars around the sky, these residuals could be produced by gravitational waves. And these gravitational waves have very low frequency and also have very long wavelengths. So they will not affect only one pulsar, they will affect a few pulsars, all the pulsars that are close by. So what they do is that they take the residuals of the timing residuals and they correlate the timing residuals. And correlating the timing residuals, when they see a correlation, they know that they have a gravitational wave coming in that direction. But these are the gravitational waves, these are the frequencies of the gravitational waves. And LIGO can detect high frequency gravitational waves. LISA can go a little bit farther, lower. And pulsar timing arrays can go to the very, very low frequencies. And the same can be done with LISA, for example. So, wow. And this is the end, and how do they look? So we know about these black holes, but many times people ask me, how do you know that they are black holes? And we actually, in all honesty, we don't know, right? So we know that they look like black holes, and we have been getting closer and closer, and every time that we get closer, we see that general relativity behaves, and all the predictions are holding, but we still cannot be sure. And this is the last effort, is to make an image of the material that is very, very close to the black hole, that is the Event Horizon Telescope. And this is an interferometer with interferometers in different continents. And basically what they do, as I told you before, with an interferometer, you take a Fourier transform of the image of the sky. And this is the amplitude of the Fourier transform. This is the baseline in units of wavelength for the emission, and these are different models. So the points are the data, and these are different models for the transfer. So this is a field disk, so this is just a circle. This is a Gaussian model, and this is a crescent model, like a crescent moon. And you can see that with the data, we already know that it's not a field disk, because if it were a field disk, the amplitude will go like this, and we see that it's not. So it has to be a Gaussian or a crescent, right? So that's the point, that's all that we can get from the very few components of the Fourier transform that we have. But if you are clever, you can actually make images. But the images require a lot of modeling. So what they did is that they make these images, and what they did, these images, they actually have 3 separate teams working on different methods to do the images. And they were not talking. So they proceed completely independently, and they make these images. They first released the image of M87, that is a galaxy that is much farther away, but it's a much more massive black hole. And you see that it's a crescent. That's the model that we have for the black hole, and these are photon orbits, and there is a lot of detail there, but I just wanted to show you the picture. And recently they released, last year they released the image of the galactic center. And they took much longer to release the image of the galactic center, because the galactic center is so complicated, and also the black hole is much smaller, so it's varying very fast. So when they did these images, they actually have to take into account the variability. For M87, they could forget about the variability, and they can integrate all the images on top of each other, so it's a much easier problem. But this one, they have to go step by step, and then combining all of them, it's complicated. And basically, this is what we are getting now. The only way, so we are already using the whole Earth to put telescopes. So the only way that you can do this better is either having satellites to get a longer baseline, or going to higher frequency. The problem is that interferometry at higher frequencies is really, really hard. But people are trying, and maybe in 10 more years we will see something very amazing. So that's it. So I wanted to show you a few things about the supermassive black holes and leave you these books, these references, so that you can look afterwards if you want to learn more. And also tell you a bit about Chile, so because I see a lot of young people here. So I wanted to tell you that we have a very large community, and I took this data from the Chilean Astronomical Society, and now we are about 278 astronomers working in Chilean universities. And this was very different in 2009 already. So in 2009, we were about 50. So the community is growing very, very quickly. We have PhD programs in many universities. I'm from Universidad de Chile, so I invite you to go and check what we have there. But if you don't want to go to Santiago or Universidad de Chile, you can go to the SOCHIA's website and find about other programs. We also have postdoctoral opportunities. I'm part of a center that is called the Center for Advanced for Astronomy and Associated Technologies, CATA. That's a center that joins faculty members from different universities all over Chile. And we also have the Fondesit postdoctorado fellowships that are actually fellowships. So you get one of these, you get a good salary, and you are an independent researcher. You need to work under the supervision of someone, but it's basically your own grant. And also, well, we have grants from the observatories. So I invite you to look at this. This is where I work. This is in the northeast of Santiago, Cerro Calán. And it's the National Astronomical Observatory, so we have several domes. Most of them are historic, but here, this is an old picture, so it's not here, but we have a millimeter wave telescope. And we use that to train astronomers and engineers. We have a millimeter wave lab, and we are part of the consortium that builds receivers for ALMA, for example. So we are doing the optics of that telescope. We also have this dome here now is used by a telescope that is detecting fast radio bursts. So these are very similar to the pulsars, but they emit a single pulse. And some of them repeat, so we are building a telescope to detect them. And we are only having it here in the city for the development part, because at some point we will move it farther away. We will move it probably to the side of Universidad Católica that has an observatory that is in the mountains. It's near Santiago, but it's much farther away from the interference. For the millimeter wave telescope, we can actually do science from there. And that's why we are building a new receiver too. We are putting a copy of the ALMA receivers there. So that's what I was asking Rita about the maps. Because one thing that we can do with this telescope is to do maps of the molecular gas in the galaxy. So maybe we can have do some high energy astrophysics from Cerro Calán. And that's it. So I hope that you all enjoyed the school. It's an honor to be here and also to be the last speaker. And I hope that you all get involved at some point in CTA when we have the telescopes. And I would like to, at some point I was talking to Farinaldo, but it will be great to have a collaboration meeting on a school like this in the telescopes, like in the site. But we will need to wait for a few years, I guess. See you soon.
I have a few questions.
Yes.
Thank you, Professor. First, you showed a picture where we have the thermal black holes and almost non-thermal black holes, something like this.
Oh, you mean the...
Yes, I think it's... And I was wondering if when we have a Schwarzschild black hole, we have a thermal one. I think it's even the beginning. Yes, basically that's the question.
Oh, thermal and thermal emission. Okay.
Yes.
So thermal emission is basically hot gas that is in equilibrium. So like, for example, a star that is emitting black body radiation. So when you have that, you don't expect to have too many high energy emission. Non-thermal radiation, for example, is synchrotron radiation because you need to accelerate the particles and you don't get a thermal distribution. You get what people call, you get a high energy tail. So you get the thermal part, but you also get a high energy tail, and that's the non-thermal radiation.
So in this case, Hawking radiation would be non-thermal.
I think that's thermal.
It's thermal.
I don't know much about that, but I think that the Hawking radiation has a black body spectrum, right?
Yeah.
That's what I think. I mean, I don't know much about that, but I think that it depends on the area of the...
Yes.
It's like the inverse of the area,
yes,
but I think
depends
that
on
it's
the
black
area.
body. But I'm not sure about that.
But
What I know is that when you have a black hole, the black hole will evaporate very quickly if it's very small, for example.
Yes.
So if you have primordial black holes, they should evaporate. And they actually tried to search them with Fermi, I think, too. And they didn't detect anything.
Yeah, but in this case, we have a kind of, because you've shown the properties of trash shield and current black holes. And in this case, a current black hole usually will be a non-thermal one, for example.
I don't think that, I mean, unless you are talking about the Hawking radiation, I guess, you can talk about the radiation of a black hole. But when we look at those, in general relativity, there is no radiation. Okay. So the Hawking radiation is not a GR effect. It's it's a quantum effect. Yes. And that part is, I mean, that's the sketchy part of physics, right? We don't know what's going on in the when you try to join quantum mechanics and general relativity. That part we still don't know how to do. Mm-hmm. But know that the general relativity solutions for black holes have nothing to do with quantum mechanics. I see. So there is no radiation there.
Of course. Okay, first I will pass the mic. Then, if I have time, I ask.
Further questions? Thanks for the lecture. You've mentioned the efficiency of black holes.
Yes.
And you've pointed that the maximum is 42%.
Yeah.
I might have missed it, but does that mean that for every solar mass that the black hole actually swells, the mass of the black hole grows by 42% of that mass?
The mass goes inside the black hole, so you are only radiating the gravitational energy.
Okay.
So if the black hole eats one solar mass, it will grow by one solar mass.
All right.
But because this energy is actually not coming from the mass, it's coming from the gravitational energy.
Okay, thanks.
Yeah.
Further questions?
Thanks for the lecture. You can also estimate the mass of the black holes using the EHT images, I think.
Yes. Yeah.
How are these estimates compared to previous estimates of the black holes of M87?
Yeah, so there were two methods. One is the one that I show you here. I show you because this is the correct one. So this one is from the stellar dynamics. That's the one, that's the good one. There is one that is like half of that, and that one turned out to be not consistent with the EHT. They can estimate it from the EHT because sort of they know, they can see this inner ring here. It's sort of like a photon orbit. So that's how they can measure the size of the photon orbit, and that's how they estimate it. And it's consistent with the stellar dynamics. They had two methods, and it's consistent with one.
Okay. And just a little question. In terms of the TV blazars, it is probably difficult to measure the mass of their black holes, but how many of them have been measured? Or
well, you cannot. For example, we show a couple of methods, right? So one of them is reverberations mapping, and for reverberations mapping, you need a broad line region, and we don't have a broad line region, so we cannot do that. We also have the stellar dynamics. But the hosts are, when you look at these black holes, you are only looking at the jets, so you cannot see the stars. The gas dynamics, these guys live in elliptical galaxies, and the elliptical galaxy has almost no gas. So yeah, you cannot measure it. I mean, you can probably get an idea from the luminosity, from the size of the host. If you measure the size of the host, you can estimate the mass of the host, and you can try to use these relationships that we have between the mass of the black hole. But these are rough estimates. It's hard to measure the mass.
Okay, thank you.
Concerning the very massive accretion disks, so it would be possible to detect gravitational waves produced
from the disk?
Yes.
I don't know. I mean, when you have gravitational radiation, you need an isotropy, right? You need a quadruple. So, for example, for electromagnetic radiation, you need a dipole, but here you need a quadruple. So I don't know if you can make a quadruple very easily with something that is so symmetric. You will need to have some spot that has higher density, I guess. And if it's not very close, so I'm not sure. But it's a good question. But I always hear people talking about, when they talk about the pulsar timing arrays and also about LISA, they talk about merging supermassive black holes, not about this. But they probably emit, but it's probably out of the reach of the sensitivity. Maybe that's what happens.
Other questions? No? So let's thank the speaker again.
Thanks.
And now we finally end the school, so the afternoon, do as you wish. Okay, some of you will return home. And I'd like to thank you so much for being here today. And I thought hopefully you enjoyed the whole week. I know it's a lot to take in, I know, but that's what a school is, okay? So it's not for you to learn, 2 years or 4 years of astrophysics and astroparticle physics in a week. And that's impossible. It's just for you to know what's going on, what's the details, what you should search for. All the slides will be on the website, and all the photos will be there on the website on Monday. So you can just go there, back up, send emails to them, bug them about the questions you didn't answer, you didn't ask them before. But that's all. Thank you so much, guys.